Okay, so hi everyone. My name is Ichi Takigawa from Japan. And the last session was very great. So everyone felt some refresh. So now we are going to get back to some machine learning algorithms. And I will be talking about the decision tree ensemble. And these are basically very simple and classic algorithms, but it's quite powerful. And let me just start by introducing myself a little bit. So my name is Ichi Takigawa, and I'm from Kyoto, Japan. And basically, I am a machine learning researcher. And my research interest is machine learning algorithm itself. And also, especially, I'm interested in the machine learning program, which include some sort of discrete structure, which is not directly trivial to how to represent that kind of structure for as an input to the machine learning algorithms. And today we will use the decision tree. So tree is some sort of discrete structures. But also sometimes data itself has a discrete structure, like genome sequences or gene networks, or I don't know, social networks or something like that. So this area is quite one of the hot topics in machine learning recently. And as well as that topic, I also working on over the 20 years for applying machine learning stuff into the natural science research, especially for life sciences and chemistry. And if we apply machine learning to that natural science, that there is a very large gap between what the goal of a machine learning and the goal of a scientist, because machine learning is basically trained on the data we have and predict the future based on the past we observed. But scientists basically want to know something new. I mean, something not in the current data sets. So there is a gap. And recently, if this is the case, we need to use a different set of algorithms. So that is the machine discovery algorithm. But today's topic is basically basics of machine learning. And here is some brief outline. And I had 2 slots today and tomorrow. And the first part from now is a focus on the decision trees algorithms. And but the entire topic is the decision tree ensemble, which means decision tree plus ensemble learning. And next part tomorrow, I will focus on the move on to the ensemble parts. And but before that, I will quickly mention about the very basics to if we have complete beginners of these algorithms. And I would use the word like trees, forest, or even stumps. But this is the technical terms in computer science. And especially this is for the data structures and like a tree shape. And I don't know why, but computer scientists draw a tree upside down. So, and I would draw a tree like this, but this is a tree, I mean, the data structures. And also, the entire topic is, I would say, the decision tree ensemble, or for short, tree ensemble algorithms. This is basically by integrating multiple decision trees in certain way called ensemble learning. So we will need to learn decision tree ensemble, decision tree algorithms, and ensemble learning algorithms. And in short, there is some algorithms for decision trees, like CART C4.5. And if we applied ensemble learning techniques to these decision trees, then we will have decision trees or decision tree ensembles, or sometimes we will say the decision forest. Forest means a set of trees. And the most widely known one, the random forest algorithms. And also we will cover some variation called extra trees and also gradient boosted trees tomorrow. But for as a start, we will make sure why we should learn decision tree ensemble from the first place. And basically tree, you will use the tree data structure as a representation of the data. So, and the tree structures are one of the, I guess, one of the most favorite, computer science favorite data structure. So you will see the tree structure everywhere, like your folders, which is file systems, and HTMLs, or class inheritance in Python or Java, and or syntax tree if we are interested in the natural language processing, or search tree, or even if you went to the library, there is a classification scheme. Library classification is also kind of a tree. So it's a hierarchical classification. And also some probabilistic model in machine learning also have that kind of hierarchy. So we will use a tree structure everywhere. But this is why we like the tree structure is simply it's very simple and intuitive and very easy to handle. So also beside machine learning algorithm, we will see the tree-shaped representation in various places. And basically decision tree algorithms we will cover from here is a very classic algorithm. I mean, I would say obsolete algorithms. And it began its research around the 60s or 70s. And it's quite popular in the 90s. But after the 90s, these techniques are a little bit unpopular due to another state-of-art algorithm like kernel method or now the deep learning. But this decision tree algorithm is sort of made a comeback now with the ensemble learning. And to make sure this one, I will make sure the decision tree ensemble is widely used in the industry as well as academics. And here is a survey of Kaggle. So Kaggle you're using now is that's basically data scientists or machine learning researchers. I don't know, SNS, like, and Kaggle did survey every year. And in this case, this is a survey result of 2021, and the respondents are around 2,500. And the question, I picked the one question, question 17 was which of the following machine learning algorithms do you use on the regular basis in industry or in, I don't know, Kagglers or some machine learning algorithm fan for some purpose. And the most popular one is linear regression or logistic regression. And probably I think you get this idea in your stat course or something. So of course, in the first several pages of the machine learning textbook covers linear models, linear regression or logistic regression. But after linear regressions, there is a red section. This is a tree ensemble or addition trees. And after that, you will see the green bar. This is for deep learning. So you are learning deep learning algorithms. But for practical side, the decision tree algorithms are more commonly used in the industry. And we will see why. But I think I will also check the last year's survey. I think you can Google the Kaggle survey or something, then you can get the direct access to the raw data. And basically, there are many questions. For example, how much salary you get in the data science industry, or what country you live in, or something like that. So you can see the stats of current data scientists. And anyway, that's why. So decision tree ensemble is one of the key algorithms in data scientist toolbox now. And I will cover some reason why this getting popular again. And the first one is a random forest algorithm, which is embedded into around the 2000s. But before or around that moment, there is a king called support vector machine, SVM. And if we write a paper, including the classification task, so every reviewer said, why don't you compare with SVM or something? So SVM is a state of the art at the moment. But there is some paper coming out around after the 2000, and it is practically shown that the performance of random forest algorithms is quite surprising. So even better than the several vector machine or even the neural network. And the first paper is targeted 11 data sets, and they tested 10 different methods, including random forest and something. And this paper is only handled at 11 data sets, but it's a quite high dimensional data sets. So it now feature is around so up to 700 kilo, so 700,000 features. But even for that extreme situation, the empirical performance of random forest was very good. So it's one of the evidence to boost the random forest popularity. The second paper is, this is actually not like a paper, it's almost kind of a references, because they are comparing every possible method, so around 180 methods with over the 120 data sets. And they compare various wide range of data sets. And then again, random forest was very good in the empirical performance. So this is one of the reasons. And another reason is popularity in the machine learning competitions. And machine learning competition like Kaggle, so you're using the Kaggle platform. And Kaggle is basically, it's originally started as a machine learning competition. So people are trying to compete by building the best model for the given data sets. And the winners get substantial money prize up to $1 million or $3 million even. So, and the Kaggle is getting popular is because around, I think, 2015 or 2017, and at that phase, Kaggle every year Kaggle did some interview for number one world rankers, and there are a few because it's a very competitive. And if we win some competition, you get the points, and if we win many times, then you can get your name on the world ranking list. And there is a number one, so champions of all data science in the Kaggle communities liked the same machine learning methods, and they named the same machine learning method as their favorites, and that was the gradient boosted trees, or GBDT for short. So we will cover this one late tomorrow. But anyway, this is one of the tree ensemble techniques, and which is a very flexible and powerful algorithms. And the third one is a little bit minor reason, but you might not know that Microsoft loves the decision tree algorithms. And there is a very strong research team in Microsoft research. And the famous outcome will be the, you know about the Kinect, Microsoft Kinect, or Microsoft Xbox 364. And Kinect, to play with the Kinect, the machine, Xbox, needs to recognize the pose in real time, because if we have a latency, then game was not fun. So if we move is not synchronized with the game, so they are very serious about how to be in the real time, the pose recognition, and that decision tree ensemble was the answer they chose, and it's performed within the 5 milliseconds per frame for the small Xbox CPU. And also, machine learning algorithms known as decision jangles or like GBM is all from Microsoft. And also, they won some learning to run, which means information retrieval, like Google search. And we can use the decision tree ensemble for improving the search algorithms. And also, this is some background why decision tree ensemble is now quite popular. And so we will make sure why we focus on these algorithms. That this is one of the three main components. So probably if you're already trying to learn deep learning, and also you are some little knowledge about the linear algorithms, linear regression, logistic regression, then the tree ensemble will be the missing piece in your toolbox. So before this, basically that today part one is I'll be talking about intuitively the inner working of these algorithms, and I want you to feel why this is good for current data sets. But before that, I will start briefly how decision tree algorithms work. So there is some very nice website here. This is entitled as a visual introduction to machine learning, but it's actually visual introduction to decision trees. And probably I think you can click around these algorithms, but just in case, I will cover this one. And also there is a translation to various languages. Unfortunately, there is no Japanese translation, but yeah, there is a quite popular in many countries. So I will make sure that decision tree algorithms are very simple and intuitive. And let's say that we have a data set like this. So in the most of the case, our data is like this one. This is a tabular data set, so Excel-like spreadsheet. We have numbers for each record. And besides that, the images or text or sound is good for deep learning algorithms. But if we have a tabular data set, then probably I think decision tree ensemble is the first choice. And here we want to predict each property here. So property in the real estate company or something. And then we just want to predict each property is in the San Francisco or is in New York. And the output is if we 0, it's for New York, and the 1 for San Francisco. And the variable we can use is other than this one in SF is we want the column we want to know, and the other is we can use for prediction. Now this is a very typical setting for supervised learning, and then we will pick up let's say the elevation variable, so single variable, and plot it like here. And because San Francisco will higher elevation compared with New York, then if we see the elevation plots, then we have some good separation. And in fact, the blue one is New York, so the highest elevation property is 73 meters. And if we cut 73 meters, and if the elevation is larger than the 73 meters, then we can predict it as San Francisco. So here there is no property in New York. So if we apply this rule to this training data set, then we can get the 64.43% accuracy, because this is all correct, but we have a wrong answer here, because below the 23 meter elevation, we will predict all of these as New York. So this properties in San Francisco will be all wrong predictions. So that's why the accuracy is 64.43. But we can move this splitting point towards the more simpler place by allowing some mistakes for New York. So let's say here, so if we set 20 meters, then accuracy goes up to 78.215%. So, but we can probably, you might think that we can optimize this split around here, and probably good balance will be around here. So allowing some mistakes for New York, but we can cover and minimize the error around here. So if we plot the accuracy here, and it turns out that between the 30 and 31 meters is the best split. So if we split here, then the accuracy is the best by one split by elevation is up to the 80%, which might good for now. So, and this is the actually decision tree algorithm did. So we pick up the one variable and search for a split and split into two groups, and then we can get the prediction. It's very simple, right? So, but this is the only one split here. This is called decision stamp. Stamp is there. So, but this is a decision tree with only one node. So, and if we see this situation in the original table, it's we did something like this one. So we have an original table here, and pick one variable, so elevation here. And if the value in the elevation is larger than the 30.5, then in that case it is go here, if go here, and if not, it's go here. So we split the table into the two tables. Okay. So this is called binary partitioning. And we split the data sets or the spreadsheet into the two different ones. And then we can do the same thing this to again for this splitted result. So pick another variable like price per square feet in this case, and then do the same thing. So find a split, and then we can get some prediction. So, and we can do the same again for this one. But if we stop here, then the decision tree. So decision tree with the 3 decision nodes here, here, here. And the accuracy is go up to the 82%. So it's not bad, right? So, and I will make sure that the decision tree algorithm is like this one. So it's very simple. It's simple to implement. Probably if you are Python primer, probably you can implement this algorithm by your own. It's very simple. And actually, decision tree algorithm is repeats this recursion until we get the desired accuracy. So if we add recursion, apply recursion again and again, then the prediction accuracy goes up. And if we stop some point, then that is a decision tree. So it should be very simple and intuitive. And also, and actually this rule is if we implemented this tree-shaped visualization in the Python code, it's nested if statements. It's very simple again, because if the elevation is some threshold, then return San Francisco, and not the case, then again we need to evaluate if the price per square feet is larger than this number, then I'll return New York, and else return San Francisco. So it's we get the if-then rule from the data sets. See, this is the decision tree. So we can get the rule. Then this rule can apply to any data set. So beyond the training data sets, right? So this rule is constructed by the training data sets, and of course the performance on the training data set is optimized. But also we can apply this to any data sets for the test data sets. And because this is just an if-then rule, if the condition of a if statement is false or true is the only place. So if we just classify true or false for each incoming outputs, then we can measure the accuracy, or we can make a prediction. So this is a decision tree algorithm. So it's very simple, right? And then this very simple ideas, where the simple idea comes from, I'll cover some little history about the machine learning about these algorithms. And actually, that algorithm is too simple. So that it's a concept so simple that anyone could think of it. So multiple researchers come up with the same idea. So it has a very complicated history. But if we organize in the 3 roots, then we can have a three section. It's originate from the something called the concept learning, or something called interaction detection in statistics, and also nonlinear regression. So we will cover one by one. So first one is learning of a concept. And as I said, this is a if-then rule. So it's logical rule, right? So then this algorithm is can be seen as getting logical rule from data sets. So and had a close relationship to the logic and logical circuit design. And other than the decision trees, also we have a decision tree, decision tables, or decision lists, or decision diagrams, and all of these is primarily related to the logical circuit of some logic. And I would say that one main program in that at that moment is a concept learning. So concept learning is if we say now, it's a noiseless version of a supervised learning, because but the purpose is basically define some concept from the data sets. Because in this example, we want to define fish, concept of fish, but the precisely define fish in the natural language is not easy, right? So it's a biologically difficult. So every concept we need to handle have this problem. So precisely define that concept in logic is very difficult. So some people started by define concept fish by examples. So in this case, there is a fish and not fish, and there is some features. And I would say that at that moment, people is only focused on the logic, getting the logical expression. So all of a variable at that moment is a Boolean. So it means yes, no features only. But anyway, if we do some supervised learning here, then we can get a rule to decide if it is a fish or not. So now, for example, if this very small data set, we can get rules something like if not has length, then is fish, because this is a pure 100% equal. But if we have more larger data sets, this task is not trivial. And I will show you some very practical, I would say the educational example from the statistics. It's a iris data set. Probably I think everyone might see this data set. It's a very traditional data set from the third Ronald Fisher defines. But anyway, so there is three species of the iris: Setosa, versicolor, and virginica. And the problem here is that we can measure the Peter here, so small thing here, and the sepal here, so length and width. And we just make a table. And our problem is try to predict the species using these four numbers. But if this table is given, it is not easy to find some clear pattern from here, right? So that's why people trying to apply machine learning algorithms or some statistical textbook, just apply, I don't know, logistic regression here or some algorithm here. But if I will show you that if we use a decision tree algorithm to this data sets, outcome is something like this one. And I will use here, I will use the algorithm called C5.0 in R, because it's one of the proper implementation. And scikit-learn also has a decision tree algorithm, but it's not slightly miss some traditional parts. So by anyway, this is just defining of the data sets, and just applying C4.5, then we get output something like this one. So C5.0 return the three rules. Now we will investigate this one in detail. So it's something like this one. So if we rephrase this rule, it's something like this one. So if Peter is here, if Peter is short, then it should be Setosa, with probability was over there, 97%. And if Peter is a white, then it's a Virginica. And if the size is the middle, then it should be the last one, the Vertical. So then probably I think you can guess which is a Setosa, which is a Vertical, and which is a Virginica. First one, we don't use the sepal, so we can ignore sepal. Only feature we need is on Peter. So this one. Okay. And then this is very short. This is a white. So it should be Setosa. Right? And this is a white, so it's a Virginica. And the last one is in the middle, then it's Vertical. And the concept here is that this rule is we can operate this rule intuitively. If you see some iris on the road, probably I think you might guess the species by this rule. And this is why the logical rule is very good at that moment. And also we can make prediction by applying this if-then rule to the test data set, and accuracy was not that part, I guess. And anyway, this is one of the one of the use case, a typical use case. And also we can try the Python code and the scikit-learn especially, and the decision tree. The scikit has the decision tree classifier and the decision tree regressor, and then we can just call it in the short code. And they can return the rule, logical rule right here, and also they can make a prediction. And I'm not going to explain the detail of the code, but if you have interested in it later, I will. I put on my slide on the own cloud folders. And anyway, you can get this kind of a fancy visualization. So for now, the first route is decision tree is for learning of a concept and the logical rules. And the decision tree is actually same equivalent to the logical rule. So if-then, nested if-then rule. This is the one rule. And this is just for information for research level. But at that moment, it's in 90s or 80s, there is a research topic called machine learning. So it's totally different from the current machine learning. It's something like this one. It's now it's called GoFi. It's a good old-fashioned AI. It's a symbolic AI, but yeah, it's something like that. So decision tree algorithms have roots in the GoFi. This is the first root. So that we move on to the second root. This is the history from the statistics. This is basically machine learning, called machine learning at that moment, at least. This is a root from statistics. And this is actually the oldest. So first paper is 1963. It's very old. And the first method is called AID. And this is an abbreviation for automatic interaction detection. And the early idea toward the decision tree algorithm started from this automatic interaction detection. So we need to briefly understand what is the interaction detection. But anyway, this is an actual paper, first page of the actual paper, and published in the 1963. But this is a decision tree, right? At that moment, this is not called as a decision tree, but it's a decision tree. And after this algorithm is invented, there is some extended algorithm, and probably I think Thide and Chide is two famous ones. I'm not sure the currently still used. I don't think people still use this kind of method, but yeah, it's quite popular in the 90s, I think. And anyways, AID, so automatic interaction detection, the name is inherited in the current subsequent algorithms. That's why this is a very important problem in statistician. And so to understand what is the interaction, we need to do some recap on the linear regression or deep learning algorithms. The very last layer of deep learning algorithm is almost always linear, right? And that is something like this one. So if we have a three variable, x1, x2, x3, then a linear model is just multiply some numbers on each input and just sum up of all of that amount. So this means that if we say that if x2 increases by 1, then it means that z output increases by this coefficient amount. So in this mean, the problem is that it has an independent effect of the value of other variables. So prediction value, so all the variables assumed to be independent. So there is no interaction here. So interdependence between variable is not considered for the first algorithm. And this is shared with the typical logistic regression or softmax regression or perceptron, any name, but linear model have this limitation. So to overcome this problem, the statistician invented the interaction term, which is basically the product term, adding product term here. So in this case, we add 3 product terms, x1 by x1 times x2 and x2x by x3 as and the like. And when in this case, when x2 increases by 1, z increases by w2 plus w23 x3. So it depends on the value of the other variable x3. So if we add some interaction term, so we can consider the interdependence between the independent variables. But if not, it's assumed there is a strong assumption. So all the variables are independent. This is a very large limitation of linear algorithms. And from the current point of view, this is a very we can see this problem as a most naive feature engineering. If we have a feature, then you can add some product term in addition to the original features. And for example, if we apply linear regression to here, then it's an ordinary linear regression. But we already observed this value in the training data sets, so we can calculate the additional columns by like a product term. So if we have a 6-variable table and apply linear regression, then interaction will be considered, at least between these pairwise interaction. So, but problem is 3 variables will be manageable. But what if we have 1,000 variables? The combination between the 1,000 variables will be huge. So we cannot handle that kind of big numbers. So if we add every possible interaction term into the regression model, it will just lead to overfitting, too much variable for given a number of samples. It's called kitchen sink regression. It's a kind of a taboo in the proper statistic analysis. And you can check the Wikipedia in the discussion. But anyway, it's in multivariate analysis, so multivariate statistics, it is necessary for the analysis to carefully select the interaction term to be included. So we cannot just put all of the possible interaction terms. So so the users needs to select which interaction term to be included. But this is not a good thing. So people might think that can we automate this combinatorial feature selection? And this is exactly what the AID is has this goal. This goal is AID's main purpose, so automatic interaction detection. So which variable is have interaction? But this method is very different from a linear regression, and it's presented in the statistical community, published in the statistical journal, and that didn't receive much attention at that moment. And also, reviewers is very harsh against this idea, faced quite harsh criticism. The first one is it just overfitting? So we should not include any tree type algorithms, and or masking problem. If there is a correlation between the variables, so if we pick up one variable, then another highly correlated variables, can do the same effect to the outputs. So we can only know the one of which from the possible correlated set of features. And also, as you see in the decision tree algorithms, it's quite simple, right? So split into the two table and apply that recursion. So it's completely ignored statistics assumption. So sample and population is a different concept, and the sample is just from the sample from the population. And what we need to care is the population, not the sample itself. So that's statistics in the traditional way. And this AID or that decision tree algorithm is completely ignore this kind of things. We are just constructing the if-then nested if-then rule from the given data set. So it should not be taking into account the populations. So that's a criticism. So this is the second route. And the third one is regression. So for now, we are focusing on the classification implicitly, but also decision tree have roots in the regression. So let's think about very simple regression here. And the decision tree, the name are you may think the decision trees are primarily for classification, but it also can be used for regression. And typical regression, so I will focus on the 1D, so one-dimensional regression problem. So it means that we are just fitting curve into the points. It's very simple, right? And the most standard method to do this is linear regression. So we are fitting line into the point, right? And if we apply linear regression to this data sets, this is a result. And clearly, this is not what we want, because these lines is not informative at all, right? So there is a many situation like this. So what we want is clearly not a straight line. So we need to somehow handle the curves. And that's why the nonlinear regression is required in that moment. And then actually, so there is some data partition-based nonlinear regression. This is a nearest neighbor regression. This is a kernel estimated regression. And this is a decision tree regressor. But anyways, these algorithms can handle flexible nonlinear regression. So we were focused on the what if we just applied polynomial regression, which means that in terms of we include the polynomials up to the several order, and that fits that polynomials to the data sets. Then if we try to fit the polynomial up to fourth order, then result is something like this. So it looks very underfitted, right? Then if we increase the degree of freedom, so we up to the polynomial order is the 10th degree, then might look better. But if we go further to the 30th order, then it's quite unsatisfactory. It's very difficult to control this kind of a parametric model to the data set flexibly. So in contrast, decision trees are very simple. So for regression trees, degree of freedom is simply control the goodness of fit. If we have a 4-tree decision tree class regressor, something like that, if we allow 10 leaves, so like that, if we allowed 30 leaves, like that. So it's very intuitive and simple to control. So that's one of the reasons the decision tree or regression tree are one of the hot research topic at the moment. And the idea of decision tree regression is very simple. And the first we might think the simplest regression models, which is a constant regression. So for any inputs, just return the constant numbers. And the constant numbers is typically the average of y value in the training data set. This is actually implemented as a dummy regressor in scikit. Anyway, it's just a horizontal line at the mean of training data sets, right? This is actually not what we want. And the problem is there is a clear underfitting here. So, but at least this is the safest prediction. So no unexpected behavior from here. Because so they won't be wrong by a huge margin. Then, but this is not satisfactory. Then the idea is basically, what if we can do the piecewise constant? So we split input space into some regions, and then for each regions we just return a constant value, so mean over that values. This is actually the regression trees. Again, it's really simple, right? So it's a piecewise constant regression. And how the regression tree algorithm works is very simple. So similar to the classification case, what we need to do is finding split points. And according to some scoring, we can evaluate all possible splits and pick the best one around here. And then our prediction value is basically average value in each region, something like this one. And the point is we do a recursion here. For example, we can apply the same thing for the left region. Then we can split into two, and then we can do a piecewise constant prediction, and something like this one. So here we have a regression tree with the 4 nodes. And basically for a regression, what we did in actual is something like this one. So for univariate data sets, this is from scikit-learn example, and just do these types of splits at some point, split into the 2 groups. And again, for each groups, we do the same thing. So this is a regression tree. And this is for single variable data. But if we have multiple variables, basically the procedure is the same. So we can pick the one variable from some variables and do the same thing. And for each point, we can pick the different variables, but the inner working is the same. It's quite simple algorithms, right? So this is some kind of intuitive understanding of a classification tree and regression tree. So we will move on to the basics of a decision tree, but the inner working is basically already described. But in detail, we need to make sure several points. So we will make sure the details for tomorrow. And first of all, decision tree have classification trees and regression trees. The classification tree is something like this one, and the regression trees is something like this one. And the difference is basically splitting criteria and the value returned at the leaf node. Because for classification, we need to one of the predefined categories. So it's returned the categorical values, like cat or dog, or I don't know, disease or healthy, or something like this one. But for a regression tree, we can return any numerical value. So each leaf nodes have any numerical values. So that's a main difference. But the algorithms to construct a tree shape structure is exactly the same. So, and then to understand that decision trees precisely, we have 3 aspects of the same algorithms. The first one is a decision tree is a nested if-then rules. That this topic is already covered. Then we will focus on the remaining 2 aspects. The first one is a second one is it's a recursive partitioning of the input space. And the third one is a little bit covered, but it's a piecewise constant prediction. So first, we will focus on the inner working. If we have this kind of data sets, and we want to classify blue dots and from the red dots. And then we will pick the one of the x2 and x1 and set some splitting points, and then recurse this one until finer grid is made, something like here. And then for each leaf nodes, we just take a majority vote. So for example, here we see some blue, but the majority is red. So if we input folder into this region, then predict it as red. So this is a obtained rule by decision tree algorithms. And as we already see, this is exactly equivalent to the nested if-then rule. Right. So point is what we need to do here is learning one split. I did not explain that part, not yet. But if we find a split point in the right way, then we can just recursively apply that split fine algorithm. So major point of the decision tree algorithm is how to find that kind of best split. Okay, so let's see iris data again. Iris have 4 variables, and if we as we already cheating, actually Peter is enough, so C variables is not important for iris dataset. But anyway, if we plot the 2 variables here, you can see a scatter plot. So maybe we want to classify blue, orange, green classes. And the actual data sets we have is something like this one, Excel table. And these 4 columns, these 4 variables is input variables. And this last column is the output variables. So we want to predict this column from the other variables. And then we put on the color on each samples, because each sample is one of 3 species. And then also we put color on each numeric values of the features. All right, and then we sort each these numerical values for each columns, something like this one. Okay, and then we pick out this single variable plot, then try to find the best split from here. And actually, the training data set is finite, so which means the splitting point is also finite. So, and I will probably, it's not easy to see, but there is some light gray line between the points. And if we check out all of these splitting point and take best one, then that we can do the decision tree learning here. And for a training data sets, probably I think we can pick any number between the points. But for test data sets, this strategy affects the results. Then the standard way is we can just pick up the exactly middle point between the points. So this is also the standard strategy implemented in the scikit-learn. But anyway, we can tweak the strategy here, but this is the standard choice. So our problem is basically, I want to make sure the decision tree algorithms, including in the decision tree ensembles, never see multiple variables jointly. So it's basically only sees each projected 1 variables. So multi-dimensional data is viewed as projecting onto the 1 dimension for each variables. And so decision tree algorithms we'll see the data set like here, not like here. So this is we can see the correlation between the variables, but the decision tree did not use that information directly. So let's say if we pick the split here, it corresponds to the axis parallel line here. So it's Peter length here, the split point around here, which means that pick up this splitting point means that we want to separate the input space along this about vertical line, so axis parallel line. So if we try this one is nice to separate the classes. And if we pick up this one, then this thing corresponds to some axis parallel line. And then we try to every possible we try every possible splitting, then pick the best one. So that's a decision algorithm, the strategies. So, and applied. So if we first split was, let's assume the first split was here, then we can split the data into the two table or two input area, and then just apply the same thing here. So let's here we can split the other variables, and we stop the recursion, for example. And but here, this is a all over sample here is a single class, so this is fine. So we stop the recursion here. There is no need to further splitting this area. So this is basically the inner working of a decision tree. So the problem is how we can find the best split here. So finding best split is learning a decision stamp, so one node split, and that is basically one of the core components of our decision tree learning algorithms. But it turned out it's a straightforward way. So just simply examining all possible split one by one. So it's very easy algorithm. No complicated tricks here. Just test every possible splits. So in this case, let's say the very simple case here, we have only two variables, and we have this small number of samples. Then all possible split means that this orange line here. So we can draw some line between the points, and all possible splits are also finite. Then we calculate some score, I will mention that later, and for each every possible split, and then pick the best one. That's finding the best splits algorithms. Okay, so, and the splits here corresponds to the axis parallel lining if we see the two input spaces. Okay, so, and if we do this one for the iris datasets have 4 variables. And this is a score, and we assume the smaller one is good. Then actually it turned out for iris dataset, we have 2 exactly same score splits, so we can pick any one of them. Okay, because first thing we want to, first rule for the iris dataset is splitting blue things out. We can split here, then only remaining problem how to classify these 2 classes. And this class is setosa. It's very simply identified even for the human eyes. So this is our first algorithm detail of the decision trees. And if we want to check in the code, you can just specify here's a max steps equals to 1 option. It's stop the recursion only once. Then you can see the first rule decision tree algorithms learn. This is the best first split. And also we can, if we use a visualization library, then also we can draw this in the fancy graphics. But anyway, this is our simple code examples. So, and we did not cover the splitting criteria. So how to evaluate the goodness of each splits. And actually there are multiple criteria. And for a decision tree classification, the commonly used one is the Gini impurities, Gini index. Another one is cross entropy, so Shannon entropy information gain. It's a cross entropy. And for regression, we can do the mean square error, the mean absolute error, and the very specific case, you can use a Poisson deviation if the data set is a count data set or frequency data set. And also I will mention later, but there is a special criteria for ensemble purpose. But anyway, there are many ones. But all over this one is basically of how the current sample is not pure, that impurity. So here, almost all sample is green, so it's not bad. But here, all of three classes are mixed together. This is a not good split. So we want to classify into each class. Then we need to put severity on this one. And for regression, it's the same. So for here, the Y value is almost same. This is a good split, good impurity. And but if variance is large, then this is not good. So all of a score is basically how to define this kind of impurities. And I just covered a little bit because this is a very textbook knowledge, but I want to, before I go into the detail of this one, I want to mention that for ensemble learning, this part is not so important. We have different techniques to define the splitting criteria. But if we want to the single decision tree algorithms, you need to care about which criterion to be used for given data sets. And the famous one is the Gini impurity and the Shannon information gain, which is as known as cross entropy. And basically, in the first example, we just use the misclassification rate or accuracy of the split, but that's not good in practice because there are exactly same scores. So we will see the many same score splits if we just use the misclassification rate because this is a discrete scoring. So yes or no, counting up the true or false or correct or wrong. So in contrast to misclassification rates, Shannon entropy and Gini impurity is a somewhat continuous approximation of this kind of direct scoring. That's why that two are measures. So we can avoid tie score in the best split search. So this is for classification. And also, these are regression, but this is probably, I think, not specific for decision trees. So I will skip the detail, but yeah, we can do just mini MSE, so mean squared error for regression. And so if basically what we want is not the criterion for the region. Actually, we need to evaluate the splits. And if we split, then we have three data sets. So the set of samples before a split, if we split, we have two sets. We have so original sample data sets and the two sets of samples after the splitting. So then the final criterion is basically comparing the before and after the splitting. And this is a impurity before the split. And this is the impurity after the split. But we have two groups and then just weighted average of two impurities. And if we split is good, then this impurity is improved. Then this is the final score for good split search. It's impurity improvement. So there are many different names, but I will use the impurity improvement here. And also, but impurity before the split is does not depend on the split, right? So it's defined on the data set we have. So we can ignore this one, and actually we can ignore this n number. It's the number of sample in the original input space. Then actually in the implementation, we just maximize this proxy score. So number of sample times impurity, sum up all over these two terms. So it's very simple. So we will cover a very small example here. If we split like this, and then the original, so the region before the split has this kind of distribution, and this region included 100 samples, and 31 black, 36 for red, 33 for green, and the Gini score is 0.665. And then if we split here, then the left-hand side have 31 samples, right-hand side have 69 samples, and they have corresponding to distribution on the classes, colors. And the important thing is left-hand side is Gini coefficient is 0 because it's pure, so only black dots is included. But the right-hand side have still we have 2 colors. Then the Gini score is around 0.5. So then we compute the impurity improvement of the score. But it's very simple. By the way, the Gini impurity is something like that. So just so for example, the original Gini score is something this one. So 1 minus the 100. So 1 minus sum to the all over class probability here. So it's around this number. And the left-hand side is the same as here. So of course, this is 0. And the right-hand side is, of course, 0.499. Then, so we can calculate the impurity improvements. So first, we need to take the weighted average here. And this is at 0.344. And then final impurity improvement for this split is at 0.321. And we just do this calculation for every possible split, and then pick the best one. That is a core algorithm for all of our decision tree learning, or even the decision forest learning. It should be very simple. So if we see the iris here, that's amount is, as we already see. So each split, we can calculate the score here, and then pick the best one here and here, probably. So as I said before, for iris data sets, first thing we should do is classifying out of the blue dots, so Setosa data sets. So this is our splitting things. So we want to next how to calculate the predicted values of the entire tree. So, and before I go it, so what that's any question for now? I guess still it's simple. Okay. So we want to make sure that compute the cross probabilities. Let's say this very simple binary classification problem of between of the blue dots and red dots. And actually, in machine learning algorithms, this problem is we put 1 onto the red dots, then we put zeros on the blue dots, and applying some curves between the 0 and 1, which represents the probability of input is input samples class is red. So, and all algorithms is basically have some surface internally. So logistic regression is something like this one. And also, for example, I will say that Gaussian process classifier is something like this one, and the random forest algorithm is something like this one. So just fitting surface, but that surface, it should be bounded into the 0 and 1 to represent the cross probability. And this is a cross probability, and we will see how decision trees or classification tree can handle this problem. So, but it's very simple. Basically, it's a histogram rule. So for this data set, we have a partition here, and then we just calculate the the mean of a y value here as that score. So surface is something like that one. So it's a, I don't know, very discrete surface. And if we pick this partition here, then we can assign class probability according to the proportion of each class in that region. For example, if we focus here, so the ratio of blue and red is 19 and 8. So yeah, something like this one. So we're just counting frequency of each classes in that region. The plot is one bar here, and then return it as a probability, class probability. And in scikit-learn, we can use this probability return by a predict_prob method. But anyways, we can return the, for example, we can choose the returning the class or returning the probabilities. But returning probability is more common, I guess. So this is a very typical typical demo code for scikit-learn's decision tree classifier. Now we can see that this fancy visualization, if we use the library called dtreeviz, I will say that covered it next tomorrow. Anyway, this plot ended in some circle graph at the end, and this represents class probability. So for this node is very pure. So all over this region is only blue, but here and here, this region, including a little bit portion of a blue sample, and this, I don't know, 25% of samples is red. So anyway, we can represent class probability in the regression classification tree. And also, we can do the similar thing for regression program. So regression is basically we want to represent numeric value instead of the discrete classes. Then problem is something like this one. We have x here, x1, x2, and y here. Then we want to fit the curve surface over this height bar. And then first thing we do is a recursive partitioning of the input space like that. And then we can count or we can average all over y values of that samples in that regions. So we can just build a bar or box bar in each region. And this is the local average of the samples in that region. It's very simple. Then we will have this kind of surface. It's not like surface, but it's a surface. So this is a regression tree, how regression tree works. And basically, this is a very conservative prediction. So probably, I think if you are using the deep learning, probably I think you will see some unexpected behavior sometimes, like the ChatGPT. It's a very flexible model with the many parameters. But the decision tree is very conservative because the returning predicted value is always some average of some subsample. So there is no unexpected behavior here. So because this is just a histogram approximation of distribution, so it's a safe prediction. And the problem is the prediction is very safer, and but we do the averaging or the very rough partitioning. So this partitioning is a sort of not so good thing, not so, I don't know, it's a very sloppy partitioning of input space. But so we made a very conservative prediction over the very sloppy partitioning of input space. That's essential of how decision tree works. And that's why this is very good for some purpose, some safety purpose. This is no unexpected behavior. So, and also this is very interesting because if we do some histogram approximation is very high dimension, then if we plot the grids or bins, but the bins in high dimension is there are many, so number of the possible bins or number of possible grid cell is exponential to the dimension. But so as a result, if we do some naive histogram approximation, there is a many cells that does not include any sample inside. But here, from the definition, each cell have at least one single sample. So there is no empty cells in the decision tree partitioning. And this is probably, I think this is trivial for you if we see the very low dimensional case. But if we come up with the high dimensional case, this is a non-trivial. It's very difficult in general. So anyway, this is a regression tree case and case example for the scikit-learn. And basically this all of leaf node plot is just how to, so we can see the variance over y in the each regions. So we can make sure that, how the decision tree works if we check out the decision tree structures and each training sample distribution at each leaf nodes. So this is a nice point for decision trees. And then we will short, so you're 20 minutes at last 10 minutes. So I will cover the remaining details a little bit. So first, the stopping conditions. But actually, the stopping condition is arbitrary. So we can set in the scikit-learn. There are many options. We can set arbitrary max depths or the max number of recursion, or max leaf nodes, max number of partitions, or minimum of impurity decrease for split or something like that. So it is very common to set combining these kind of constraints directly. So in the typical cases, basically classified like a 3 category. We can stop the recursion based on the size of the tree. So 2 large trees are not referred, then we can stop there some points. And then stop on the impurity. If we see the no implemented impurity, we can stop the recursion, or we can safeguard by the number of sample in the leaf node. So if we don't want to region containing only single sample, then we can set the, 2, then at least each region includes 2 samples. And this is a directly controlled ones. And probably I think a major one is, for example, the combination of the 2. One is a max leaf nodes, which control the size of the tree, and another is a min sample leaf, which prevents the fragmented regions. So, but you can try any combination here. And I want to make sure the scikit-learn's default is grown fully, which means that they do the recursion until the training error reached 0, which means most of the cases it's overfitted. And this is a default parameter of decision tree classifier and decision tree regressor. So you should check them if you use this in the realistic situations. And what this means is more intuitively, we can have a 0 training error even for the random input and the random outputs. Now, this is some example. If it sets X inputs is a completely random, the Y also complete random, then accuracy is 100%. So there is no training error. That's this is a strange. So there is no clear way to. There should not exist. There is a way to predict something random from a something random. So this should be not correct. This is just overfitting. But please take care about this default setting. Because now why this is a default is a primary decision tree classifier or decision regression classifier is used for ensemble. I will explain it tomorrow. But if you use a single decision tree, please take care of these defaults. And also, I will pick up, I will skip a little bit. And basically, that algorithm I explained is very greedy. So for every split, I pick the best one, and the split one, I pick the best one. But this ignores the entire optimality, right? So, but this problem, if we search all possible decision tree, and that problem is known to NP hard. So it's infeasible, time consuming. So that's why that that greedy method I described is a standard approach even for now. But there is some research on the exact algorithm. And also we need to control the complexity of the decision trees, as you already see in the deep learning models. So if model is too simple, it will be underfitted. But if we apply that if model is too flexible, then we will see the overfitting here. So we need to do something good in middle. So this is basically decision tree, and there is a very traditional way to do this. That is called CCP, so cost complex deep learning. And basically, as in I'm not sure deep learning course cover this one, but not only minimizing prediction error, we also add some penalty here. So if the number of leaf nodes means if we have many leaf nodes, it means the tree is huge. So if to prevent generate the huge trees, we put the penalty of the number of leaf trees, and put some regularization penalty term here, alpha here. And this is actually implemented in the scikit-learn as an option CCP alpha. And basically, this is called pruning in decision tree. The pruning means very simple. If we prune some leaf nodes or some edges, which means that just revert to the state before this split occurs. So just revert, so concatenate samples and stop here. This is a revert state, and the algorithm works this one. So if we start the fully grown tree here, then we evaluate the all over leaf nodes. And if we revert it, then the increase in the prediction error is just, we pick the one which have the increase in the error is the smallest one. So and then we can pick the smallest one here. Then we can make a series of trees, and some mathematical theorem guarantee that there is a single unique solution in somewhere in these sequences that minimize the score. So that's a cost complexity pruning. So it's quite simple. That generate these three, and if we that some score is best, then that score is a best one for the given scoring. And meaning I want to just make sure the advanced topic a little bit, but actually if we see what I told today is you might think of something like this one. So we need just bipartitioning of space and some prediction at the leaf node. And then, for example, this is not always not necessary to be restricted on the axis parallel surface. So we can, for example, we can do something like this one. And for each leaf region, we can build any machine learning model for here. But this idea won't work. So, but there is a many research, and especially the first thing many people tried is replacing the leaf node constant is not good idea, right? So replacing leaf node constants by linear prediction. This is called model trees. And another type of natural extension is axis parallel splitting is not flexible. So instead we use the general linear splitters here. But anyway, this won't work. We will see why this won't work tomorrow. But anyway, this is a final remark today. And there is a very famous textbook from IST, Chipsler, and Friedman, and they argue about all of all the well-known machine learning algorithms, decision trees comes closest to the meeting the requirements for serving as an off-the-shelf procedure for data mining. Because only trees have a very good point. I will skip the details of, for example, we can have a natural handling of a mixed type, so we can naturally handle the numerical data and the categorical data. And also there is some special algorithm for handling the missing values. And also we we are just comparing the order, so splitting points, and then we see just the subsample is larger than the split or smaller than the splits. Then it's insensitive to a monotone transformation input. So for deep learning method, probably I think you might have to try many possible pre-processing, normalizing the pixel values or applying standardization, or sometimes we need to take logarithm to the input or something like that. But there is no need for that kind of pre-processing for decision trees. So anyway, this is a very good algorithms. So this is basically final remark for today's parts. And tomorrow we will start. It looks good so far, right? But this algorithm has a huge problem if we want to use it in the practice. So I want to start that topics tomorrow. So anyway, so some question for today? No, it's okay. Okay, thank you.